Okay, good morning, everybody. I'm Chris Scalise, the NASA Associate Administrator, and it's my pleasure today to be able to introduce this technical seminar on the challenges and progress and development of shape memory alloys for solid-state actuator applications in aeronautics. It's a long title, but it's a really interesting topic. I've used shape memory metals in a number of the designs of spacecraft and instruments that I've been associated with, so I'm looking forward to really hearing it. And you probably have used many devices that may have some shape memory metals in them. This is obviously a much more capable, state-of-the-art discussion than what you've heard or used or may have seen before. And here to discuss it is Dr. Ron Noby. He's a materials research engineer in the Advanced Metallic Branch at NASA's Glenn Research Center. He has more than 20 years' experience in the design, development, modeling, processing, characterization, and application of structural and advanced functional alloys with experience in high-temperature ordered intermetallic shape memory alloys, which is what we'll be talking about today. He leads a team that in the Fundamental Aeronautics program, where they investigate and characterize high-temperature shape memory alloys to accelerate their application in aerospace and other industries, which is something that many people don't realize how effective we are in exporting the technologies that are developed here into real practical applications and getting them out. So it's a very important activity that we want to produce. In addition, Ron has co-authored more than 300 technical publications, including numerous book chapters and more than 100 papers in peer-reviewed journals. He has 5 patents and is a fellow of the American Society for Metals, so he's certainly very highly qualified to talk about this, which is why he's here. So please join me in welcoming Ron, who will discuss NASA's latest work in this field. Ron?
Thank you, Chris, and I apologize for that title. It is a little bit long. If we could have the first slides for the seminar. I want to thank you for that introduction. This seminar might be a little bit different from a lot of the seminars that you've heard previously for ARM&D. It's not one of the it's not a large systems level overview of something that's going on in aeronautics. It's not one of the high visibility research programs that's going on. It's really more of a low-key technology. It's something that really works behind the scenes. But it could be someday a very important enabling technology. And it kind of reminds me of the situation. There was an old, I think it was ADM, Archer Daniels Midland had a commercial that went something like this. We don't make a lot of the products you use. We make a lot of the products you use better. Well, if I could have the first slide, please. That's the way I view shape memory alloys. All right, we don't make inlets, but we make them with shape memory alloys where they could be basically a variable geometry configuration. We don't make nozzles, but we make variable geometry nozzles. We don't make chevrons, but we make them adaptable. We don't make blades, but we can make them reconfigurable. In fact, we don't make a lot of the different aerodynamic surfaces, flaps, vortex generators, tabs, that kind of thing. But we can make them adaptable and smart. Now, the reason for doing that should be obvious to everybody in this audience, but if I could have the next slide, please. I'll just review it for cursory purposes. Really, if we had, today aircraft are really designed to operate at a fixed operating point, but if we could change the aircraft so that we could reconfigure it for different points along the flight envelope by taking major components and having them match their geometry, form, function, to better be able to optimize their performance along different parts of the flight envelope, so the whole aircraft is better equipped. What you're going to do is obviously get better performance out of your aircraft. And because of that, you'd obviously lead to reduced fuel consumption, which is something we need today, as well as reduced emissions. Because of that, you'd also be working with larger operating margins, so it'll give you a greater margin of safety. And it's one of the few technologies where you can actually use to basically reduce noise in aircraft today. basically doing things for reducing noise on takeoff, and then you can use adaptive technologies to get those out of the way as you go into the cruise configuration so that you don't lose or take a penalty on performance. We're already beginning to do that in some of the aircraft. Fighter aircraft have variable area nozzles. You have the V-22 Osprey, which has the tilt rotor capability. But if we take the example of the V-22 a little bit further, if you could just change the twist on the blades by about 2 to 3 degrees as you go from vertical takeoff to horizontal flight, if you could just get about 2 to 3 degrees additional twist in those blades or change, you could get another 120 nautical miles out of the aircraft. So this is the type of reconfigurable systems that we're talking about. The key to all this is better actuation technology, and this is where another point where this talk is going to be a little bit different than most. It's actually a material science talk, because that's what I am, that's what I know. If I talk about anything else, I'll really screw up. So it's a material science talk, but I'm not here to talk about the next generation of superalloys, a 5th generation with 10 degrees better creep resistance over a 4th generation alloy. My competition isn't another material. They're conventional actuation systems. So while I'm talking about a material, what I'm trying to do is replace things like conventional hydraulic, pneumatic, motor-driven systems, solenoids and the like. So if we could have the next slide, please. Some of the advantages of shape memory alloys as actuators, the different advantages basically come about through 2 primary properties. One is that they have a very high energy density. The other one is that they're basically just solid state. They're a chunk of metal. From that, you get a number of advantages that can be derived from these. The primary one being basically a large amount of force that you can get from a very small volume or weight of material. The example on the right is something that Boeing has been working on. The bottom figure is an SMA actuator made up of a pair of torque tubes and a shuttle mechanism. It's capable of generating about 150 inch-pounds of torque and weighs about a pound. Now, if you went with a regular type of a motor or gearbox system, to get the same kind of torque, you would have to increase the weight by at least an order of magnitude, if not more. So shape memory alloys give you basically a lightweight, compact way of performing actuation. And what happens is that because of that, they're easily integratable onto existing systems. Boeing's very interested in working with shape memory alloys because they can fit them on existing aircraft to get actuation where you could never do it today with conventional actuators. With shape memory alloys, you get to eliminate a lot of the extraneous systems. You don't have all the associated systems with hydraulics, pneumatics, and mechanical systems. They're robust because you're really just talking about a chunk of metal. They're very simple, frictionless. They're also a quiet form of actuation. In fact, BMW uses shape memory alloys to move their side mirrors in their cars, because anybody that's paying $50,000 or $100,000 for an automobile doesn't want to hear an engine turn or a motor turn on when you try to adjust the side mirrors. So in that case, it's very important. They're low maintenance, again, because they're very simple. In general, they're very low energy because they respond to a change in temperature, and whatever it takes to put together or implement that temperature change is what it takes to actuate these materials. And in some cases, you could use that to your benefit to work these materials passively, where a change in temperature would actuate something, some type of a flow device or a door or something. And in that case, you can eliminate additional things like sensors and electronics to your systems. They also can be, and the way they're most actively used, or most commonly used, is for active control for high force and precision movements. And in this case, in general, we're talking about then, shape memory alloys are very ideal for what would be high force, large stroke actuator requirements, but for very low duty cycle. Because you have to put heat into and out of these systems, you can't use them with a very high frequency, only the frequency at which you can basically put heat in and out of the system. If I could have the next slide, please. Now that I've hopefully sold you a little bit on the technology, what I'm really going to talk about today are really 3 things. One, I want to give you a background in shape memory alloys, talk about the mechanism behind the behaviors that I'm going to show you today, give you a little bit of terminology that will help you understand the rest of the talk, then talk about some of the work that we've been doing at Glenn Research Center in the development of new shape memory alloys for higher temperature applications and what we've learned along the way there. And then finally, just talk about the application of some of our high temperature shape memory alloys And not so much as to point out the different applications, because I've pretty much already done that, but to show how you can integrate and what it takes to integrate these materials into various components. So if I could have the next slide, please. Starting with the fundamental behavior of the materials, shape memory alloys, if I could have the next slide. What shape memory alloy is a very descriptive term. Basically, it's a very special type of a metallic material, a very unique metallic alloy, that when you deform it at some low temperature, it'll remember its original shape before you deformed it, and then it'll actually recover that shape when you heat it up. So if that's not descriptive enough, if you could run the first sequence for me, please. This is an example. If we could go ahead and run the first video, please. This is going to be an example of just shape memory effect. I think we already got halfway through that before we started. What we have is, if you could repeat that, please, I'd appreciate it. I'd like to have the video one more time. We have NASA kind of spelled out as the NASA worm, and we basically can deform that, pull it apart, destroy it. But as you heat it up, you'll basically get it back. So even though we spend a lot of time eradicating the NASA worm from NASA, sometimes it just keeps coming back. If I could have the next slide, please. The origins of the effect that you've just seen are related to a particular type of phase transformation. It's a thermoelastic Martensitic transformation that occurs between a high temperature phase that we refer to as the parent phase or the austenite phase and a low temperature phase known as martensite. And there's a number of characteristics that are necessary in order to produce that effect. This is not an inclusive list, but it's some of the more important. First of all, the phase transformation itself has to be reversible, and that's pretty much what thermoelastic means. It defines that. A thermoelastic transformation is one where the energy for plastic deformation as well as the interfacial energies are negligible. So what does that leave you? Well, that leaves you the chemical energy for the transformation, which is a function of temperature, and elastic energy. And if that's all you're considering, then your transformation can be reversible. A Martensitic transformation implies a diffusionless phase transformation. So the atoms themselves move less than one atomic space from their original position, but they tend to do this in a coordinated movement. The parent phase, or the high temperature phase of these materials, is always an ordered compound, and that's important in order to get the shape memory effect because it has to do with the reversibility and not being able to break the order of the material, because that would cost a lot in terms of additional energy. And then there are particular orientation relationships, usually between the parent and the Martensitic phase, so the least common planes, so you can have a reversible phase transformation. If I could have the next slide, please. As I said, the transformation itself is thermally induced. There are 4 characteristic transformation temperatures. So if you start at the highest temperature, when you're fully austenitic and you begin to cool the material, you'll first hit a Martensitic start temperature, or the MS temperature. That's the temperature where you first begin to form martensite. Then there's a Martensitic finish temperature, or MF temperature. That's the temperature at which you're now 100% martensite. So that's the direct transformation. The reverse transformation would be the transformation on heating. So if you started with fully martensitic material and heated it up, you would first hit the austenitic start temperature and then an austenitic finish temperature. Between the direct and the reverse transformation, you have a hysteresis, and that hysteresis is due to the fact that you do have some elastic strain that you have to overcome in the material. So you have to have some additional either undercooling or superheat depending on what direction you're going. Now, if I could have the next slide. I talk about this high temperature parent ordered phase. It's almost always a B2 ordered compound. B2 ordered compounds are generally binary compounds composed of 2 different elements of equal atomic composition. In this case, the most common shape memory alloy is nickel titanium, so you'd be referring to something that's very close to 50% nickel, 50% titanium. The structure itself, you would think of it as a cube with the one type of atoms on the cube corners and the second type of atom, for example, titanium in the center. Now, the top row of figures are all just examples of the various, it's just the same, they're similar views of the same thing. It's all the B2 structure, but different versions of it. If you take the center section, you take 4 cubes and put them together and take cuts along the 110 direction, and those are outlined in red on the slide. What you'll end up with, and you pull that out, you'll end up with a face-centered tetragonal cell. We haven't done anything yet. This is still the original crystal structure. We haven't done anything to it. We're just looking at it in a different orientation. But if we take that cell now and shear it, and if we take the take the bottom and top layer of atoms and the middle layer and shear them with respect to each other, what you'll do is create an orthorhombic structure, also known as the B19. And that's the martensitic structure of a lot of the high temperature alloys that we'll be talking about later today. Now, if you take the B19 structure and shear the front and back face so you now have a non-90 degree angle, you've created the monoclinic structure, and this is the typical crystal structure of nickel titanium, and it's also referred to as a B19 prime structure. Now, this is just an exercise in crystallography. It doesn't tell you anything about how the atoms got from one position to the other. It's just showing you the orientation relationship between them. If we could have the next slide. This is a model proposed by Nick Hatcher, who's a student at Northwestern University. He's also working with us as a GSRP student, developing low-energy transformation paths in the nickel titanium, as well as some of the high-temperature nickel titanium ternary alloys that we have. And this is one of the models that he's developed as far as the movement of the atoms that are involved. And this was calculated using first principles calculations and determination of gamma surfaces. But if we start again with the original B2 unit cell in the upper left-hand corner there, and we begin to rotate it so that we're looking down only on an 011 perspective of the cell. That would be the bottom version, or the bottom view there. You really have 2 layers of atoms, so you have to take that into account. We go to the figure on the right. If we take that orientation that we're looking at and put in a shear along 100 directions, and this is a bilayer shear, so every 2 layers of atoms will move with respect to each other. And we allow the nickel atoms and titanium atoms to relax. Nickel move closer together, the titanium atoms will move apart. And we continue that shear to about a half of an atom spacing. What you'll end up with is a material with about 109 degree angle with it. Then if we allow that to relax back to about 99 degrees, you'll get the martensitic structure. On the bottom is the energy for that particular movement of atoms, and as you can see, it's a continuously decreasing barrierless path for the atoms, and this is just then one of the views of how these atoms actually move. Now, if we can have the next slide. So far, all I've talked about is the effect of temperature on the phase transformation itself. But in order to look at the shape memory effect, we have to start looking at it in 3 dimensions. We have to add stress and strain to the equation. And so in order to understand the mechanism behind the shape memory effect, I'll just walk around this slide starting at point 1 and working clockwise around the figure. If we start at point 1, we're at some high temperature under stress-free conditions where the material is fully austenitic. Under those stress-free conditions, if we allow the material to cool, will form what's called self-accommodated martensite. What that means is that there are a number of different variations or variants of martensite that can form from the original austenite. In 2 dimensions, I don't know if it's clear on the screen, but you can see 2 variants in 2 dimensions. You have a variant shifted to the right and a variant shifted to the left. In 3 dimensions, you'd have 24 different equivalent variants in those materials. And what happens is that you form all these different variants very closely together so that when you go through the phase transformation itself, you get no bulk change in the shape of the material, even though you have a slight volume change due to the transformation itself. So if we take this self-accommodated now martensite and deform it, that's what you do. You begin to deform the material, say at room temperature. You start forming D-twin martensite. And what that means is that you take the self-accommodated martensite that's there, and you're going to either take certain variants of that and it's going to reorient, or certain variants are going to grow at the expense of others so that you have fewer but now D-twinned martensite, which is the figure in 3. So as you deform the material, you release the stress then. That new shape that you've just formed will be stable and nothing will change. You've got a deformed material. It's only then when you heat the material back up will the material then transform back to the original austenite, and in so doing that D-twin martensite comes back to that original variant of austenite. And that's really the mechanism behind the shape memory effect. If I could have the next slide, please. I'm going to go through another example of this, not schematically now, but talk through the shape memory effect in terms of the behavior of shape memory alloy spring. So first of all, you have to realize that this spring was shape set. That means the shape for the spring was set at a high temperature. So the spring shape is the high temperature shape for the spring, and then we've cooled it back down through room temperature and formed the self-accommodating martensite. So if we could go ahead and start the movie then. We've got the self-accommodated martensite. We go ahead, we pull on the spring. In this case, unlike normal springs, it doesn't come back. We've de-twinned the structure in the material, but as soon as we heat it back up, it comes back to the original high temperature shape, which is the spring shape. So this is just a view of going through what happens here. Again, you deform the spring, nothing happens. It stays in its original shape, de-twinned, but as you heat it up, it comes back to the original spring shape, which is your high temperature shape. Can I have the next slide, please? This is still only part of the equation of what we're talking about if you want to use shape memory alloys as actuators. Unfortunately, this is about as far as most people go. They measure shape memory effect, and all that is a change in shape under stress-free conditions, but that's not going to do work for you. If you want to do work and use these materials as an actuator, what you really need to do is harness them some way or have them work against some type of a load in order to act as an actuator. For example, if you run the next video, now we're going to go back to the spring, but instead of just letting it freely recover, if we hang a weight on the spring, which you can see on the bottom, and you heat the material up, it'll return its shape, but at the same time now it's pulling a weight, so it's doing something. You can have this spring then open a latch, move something, and then as you cool it back down, the material or the weight de-twins and pulls back the spring. So now you basically have what's called a biased two-way effect. You're going to have the weight basically de-twinning the spring and doing work on the spring, but then when you heat it back up, you can go ahead and pull the weight, and so you have this basically a biased two-way effect, which is how shape memory alloys are usually used. If I can have the next slide, please. If those are the properties that you're interested in, then you're interested in properties where the shape memory alloy itself has some kind of a constraint on it. So you really won't want to measure then the thermomechanical properties of the shape memory alloy. So in order to do that, you run what's called a load-biased thermal cycle. So you'll take the material, apply some type of load on it or some type of a constant stress, cycle the temperature and measure strain. And from that strain temperature response, what you'll get are almost all the properties that you need to understand these materials. You get all four characteristic transformation temperatures. You get the transformation strain, which is one of the most important factors here. And because the transformation strain is directly proportional to the work output, it also tells you the type of stroke you're going to get in the materials. And you also get something known as irrecoverable deformation if those loops don't close up. Now that's a bad thing if the loops don't close up, because what will happen is with continued cycling, you're going to grow your actuator, and if you have very tight constraints, you're going to run the actuator past those constraints and it'll no longer work. Or worse yet, what's going to happen is you're going to set yourself up for a low cycle fatigue condition, and the sample will fail relatively quickly. If I can have the next slide. One of the real bones of contention with the shape memory alloy community is that all they usually do is measure shape memory behavior. They don't do it under any kind of load biased condition. Now this is an example of two of the alloys that we've been developing. They're platinum based. It's a nickel to titanium platinum based system. The only difference between the two materials is that one of the systems contains 20% platinum, the other contains 30%. This is the stress-free shape memory behavior of those two particular alloys. We've loaded them both at room temperature, removed the constraint, allowed them to recover elastically. We still have a certain amount of deformation. As we heat the alloys back up, we get the shape change due to the shape memory effect, and by the time we get back to room temperature, we've recovered all the strain that we initially put in the material through both elastic and shape memory behavior. Now if you go to the next slide, This is the behavior of these two particular alloys under some type of a load bias condition. The material on the left, the 20 platinum alloy, shows very good work characteristics, very good closed loops. The material on the right has zero work output. Absolutely no work output for that material. So just measuring the shape memory behavior itself is not going to give you any indication of how these materials are going to perform under actuator type applications. So if I can have the next slide. The point is that this is about as far as most people go. They measure shape memory behavior, but that's not sufficient, especially in the case of the high temperature shape memory alloys, because it's not indicative of how the material is going to react under stress. So if we could have the next slide. What I'm going to talk about now are some of the challenges, besides the fact that nobody measures the correct properties for these materials, to basically developing high temperature shape memory alloys. So if we could have the next slide. Let's say we wanted to take and make an actuator that was going to work at 80 degrees C in some environment and open up a flow valve. If we wanted to do that, the first thing you'd try to do is go out and buy a shape memory alloy. Now, there are a number of companies or primary producers for shape memory alloys. The two main ones in the United States are Seis Getters, which just bought out Special Metals, Nitinol division, and Huacheng. In Japan, in the Orient is Furukawa, and again in Europe there's Seis Getters. Those are primary metals producers that produce the original ingots of shape memory alloy. Those can be sold to dozens of other secondary producers that then fabricate the various foils, rods, wire, tubes, and other shapes for the shape memory alloys. But if we went to, say, Huacheng and we asked them for their highest temperature material, they would sell us 100 C material. Now, the reason is that you can actually get shape memory alloys in a number of different for use over different transformation temperatures, because the transformation temperature itself is a strong function of stoichiometry. So if you look at the inset, the transformation temperatures at 50% titanium and above are more or less constant, but the second you go nickel rich in these alloys, you start to have a very significant decrease in transformation temperature with increasing nickel content. So you can actually get shape memory alloys or buy them with various transformation temperatures. And in fact, the companies won't sell them to you based on composition. They'll sell them only to you based on transformation temperature. So they'll actually just produce large ingots, measure the transformation temperature because it's such a steep function, and sell you the material you want. So let's buy the 100 C material that Huacheng will sell us. If we have the next slide. Hopefully I've convinced you by now that the thing you want to do is go ahead and do these load biased thermal cycles. So we go ahead and we thermally cycle this material under load. And what we find out now is that all of a sudden, if we wanted to use this material at 80 degrees C, we could use it one time. We could actuate the material once, but we could never reset it. Because remember, there's 4 characteristic transformation temperatures. And they sell you the material by the austenite finish. They sell it to you by the highest transformation temperature. Now, they do that for reasons because most of the alloys are sold for the biomedical community for superelastic applications. But for actuator applications, you want to know what the Martin Sig finish temperature is. So you would want to know where the MF temperature is, because you would like to have your environment below that in order to turn your actuator on and off. The other problem with this material is that after you cycled it even just 10 times, you've grown it in length by about 1% due to that irrecoverable deformation that we were talking about earlier. So a couple of things here. First of all, when they talk about high temperature, and this is considered a high temperature binary alloy, high temperature is relative because you could basically use this material just above room temperature. The other problem is the stability issues. So what other options do we have? Well, today there's no other commercially available shape memory alloys. Basically, all you can buy are nickel titanium alloys. Years ago, you used to also be able to buy copper-based alloys, but they were basically microstructurally unstable, and they didn't have as good of work characteristics, so they no longer are sold. So that actually kind of frees us of constraints. So now, since we have nothing else available to us, what can we do? We'll go to the lab and make our own alloy. So what are our choices? If I could have the next slide, please. This is just a list of the various high temperature systems that display martensitic transformation temperatures. This is part of a review that we're working on with Texas A&M University. There are a number of different alloys with the transformation temperatures shown on the right and the stress-free transformation strains shown on the left. Now, I just told you that stress-free transformation strain is more or less meaningless. And it is. It still is. The only problem was there wasn't one single data point anywhere in the literature that was done under load bias conditions. This is all that's available to us. So we can't use that as any kind of a discriminator. If you look at the list, there are a number of material systems there that you wouldn't want to work with, such as the uranium-based ones. There are other systems that are not microstructurally stable. There's a couple of high-temperature systems that are not environmentally stable under the conditions where you see the transformation. A lot of these materials are not processable, so if we start eliminating systems, about all you're left with are the ones that are derivative nickel-titanium alloys. And why not? Why not stay with what you got? What got you here? The best shape memory alloys are nickel titanium, so you might as well work with a derivative structure. So if we could have the next slide. If we take out now all the nickel titanium systems, the ternary systems that are available, they're plotted here as a function of ternary alloying content. So basically what we're talking about now is taking out nickel and adding either palladium, platinum, or gold, and you'll get an increase in transformation temperature. Or if you take out titanium and replace it with zirconium or hafnium, you'll get an increase in transformation temperature. And you can get transformation temperatures in these systems as high as 500 to 1,000 degrees C. So you can have some very high temperature shape memory alloys here. Again, the problem is, what else do we have to go on to narrow down this selection of alloys? And the problem is there really is nothing else. Other than when we first started working in this area, other than one data point for a nickel titanium hafnium thin film, there was no load bias data available for these. So if I could have the next slide. What we did was we immediately went out and made a series of these high temperature shape memory alloys of varying compositions, and that gave us various transformation temperatures. And the only thing that we measured then was basically the work output for the material. We didn't care what any of the other properties are because we wanted to kind of screen these very quickly and find out what was going on. So the data points here actually represent the transformation range for the particular alloys. So at one end of what looks like an arrow bar would be your martensitic finish temperature. At the other end is your austenitic finish temperature. And that's the full range of the transformation itself. And we plotted the points as a function of maximum work output that we could get. And what we found was that we could get fairly good work output out of these materials up to about 300 degrees C. A typical binary nickel titanium alloy is going to give you a work output also on the order of somewhere between 8 and 14 joules per cubic centimeter. Though under very special conditions and specially processed, I've seen a binary alloy as high as 20. For the most part, we're doing very good. We're doing what typical nickel titanium alloys will do in terms of work output. The problem, you see, is that even though these things have transformation temperatures up to 1,000 C or so, the work output's only good up to about 300 degrees C, and once you exceed that temperature, your work capability drops off significantly. By the time you hit 500 degrees C, you have no work output at all from these materials. So if I could have the next slide. The challenge here is twofold. One is to figure out and understand why you have a temperature limitation based on work output, and then going back to one of the original slides on the binary alloy, the dimensional stability issue. And what we needed to understand was what drives these characteristic behaviors. So we did this studying a nickel titanium palladium ternary system. If I could have the next slide. What we did was we created a series of alloys, basically constant titanium level, and we replaced the nickel with 15 to 46 atomic percent palladium. And that gave us a series of nickel titanium palladium or ternary alloys with varying transformation temperatures. If I could have the next slide then. What we did, the first thing we did then was measure the work characteristics of these materials. And again, this is the strain temperature response at various constant stress levels and the equivalent work output for the alloy containing 30% palladium. And we did this for all the materials. And that is summarized on the next slide. If I could have the next slide, please. This is a plot then again of now strain versus transformation temperature. The bars again represent the martensitic finish to the austenitic finish transformation temperature. This is all at a constant stress of 300 MPa or 295 MPa. And we've got transformation strain, which is proportional to your work output, plotted as the top line for the various palladium-containing alloys. And you can see you get a slight decrease in transformation strain with increasing palladium content or increasing transformation temperature, but at some point it drops off and it just falls to zero. Likewise, with the permanent or irrecoverable strain, there's a slight increase with increasing palladium content. And again, you finally get to the point where at the 46% palladium-containing alloy, just loading the material up and heating it up to that transformation temperature causes the material to fail. So if you want, go to the next slide, please. What we needed to do is characterize the behavior of the individual phases, right, both the martensite and austenite, figure out what was going on in terms of their mechanical behavior. So we just ran isothermal tensile tests on the martensite, and we did that at a temperature of the MF minus 50 degrees C and got stress strain curves. In this particular case, what looks like a stress strain curve, the yielding here is actually represents the onset of the detwinning process in these materials. So it's not what you would conventionally think of in terms of yielding. For the austenite condition for these alloys, we tested the materials at the AF temperature plus 50 degrees C so that it was fully austenitic. And in this case, yielding is associated with what you would normally think of as permanent deformation due to dislocation processes. And what you find is you get a slight decrease in the yield strength of those materials or those alloys with increasing palladium content until you get to very high levels and very high temperatures, and the strength drops off to very little, next to nothing. And that more or less makes sense. I mean, as you go up in temperature, things get weaker. It's easier to see it in the next slide. If you plot this data now as critical stress versus palladium content, we now see that we have the austenite yield strength in more or less red, as well as the martensite detwinning stress in blue as a function of palladium content, and that's just proportional to transformation temperature, either way you want to look at it. At some point, those two curves cross, and that's not a good thing. What happens then, or what that implies, is that where those curves cross, it takes more stress to detwin the material. And if you can't detwin the material, you have no strain to recover back. So it takes more stress to detwin the material than it does to permanently deform the austenite condition of the material. So right around 350 degrees C, where you see this big drop-off in behavior, is where you get this crossing of the two plots. However, this doesn't explain necessarily why you get this irrecoverable strain in the materials or these alloys. And so we've forgot one component to this, and that would be the permanent deformation behavior of the martensite phase. And this is a little bit harder to back out. And if we have the next slide, what we had to do in order to back out the permanent deformation of the martensite is go through and do these step tests doing shape memory behavior on the material. So what we did was essentially loaded up the samples to a given strain, unloaded to say 0.3. We've released the elastic deformation in the material. We then heated the sample up through its transformation temperature. If it came back to the starting point, great. We fully recovered everything. If it didn't come back to the starting point, the difference between basically 0.1 and 5 would be the amount of permanent or irrecoverable deformation that we induced in the martensite itself. So if you go to the next slide, it's just a series of loading and unloading curves, though we only have unloading curves shown every 10 cycles for the material. We start by subtracting off the elastic deformation, so we have basically a plastic stress strain curve. As we heat the material up through the transformation, we cover things, the shape memory strain. What we're left with, and subtract that off, is a curve that represented by that red line, which now just represents the permanent deformation of the martensite. We've subtracted out all the deformation processes that are recoverable, elastic deformation and shape memory behavior. So basically we have like a pseudo stress strain curve for permanent deformation of the martensite. If I go to the next slide, please. So what that gives us now is a series of stress strain curves for the permanent deformation of the martensite, and from those we can go ahead and pick off more or less yield strengths from the material, and we plotted that on the next slide. So if we add that data now to the master plot, what you see is that we have the stress it takes to induce permanent deformation in the martensite is very close to that required to detwin the material. And it's, the way we picked off the points, it's actually a little bit closer than what's even shown here. And as you go up in palladium content, those curves get moved closer together. So what that implies is that as you're trying to detwin the material, you're also inducing permanent deformation at the same time. And that case gets worse with higher palladium content alloys. So what we learned from this exercise, if I could have the next slide, is that Even though you have a high transformation temperature, that doesn't mean that you're going to have a very useful material at most temperatures. And what we found was that the practical limits for these alloys, the high temperature shape memory alloys, the properties were basically dictated by the mechanical properties of the behavior of the individual martensite and austenite phases. If I could have the next slide. What this also gave us, though, was a set of design criteria now, something we can actually wrap our hands around if we wanted to make new alloys. Basically what it says is that you want the detwinning stress to be as low as possible. You want to be able to easily detwin and recover deformation. At the same time, you want to make it very difficult to get permanent deformation of both the martensite phase as well as the austenite phase. And I'm not really sure how to handle the first one metallurgically, but the second two processes, that's basically blacksmithing 101. To make the material stronger, what you want to do is just either thermomechanically process the material, cold work it in some way. You could add alloying additions for solid solution strengthening, or you can do something to induce precipitate strengthening. So that's what we've done with some of the high temperature alloys. If you go to the next slide, this is one of the more recent results we have on microalloying of the nickel, titanium, palladium alloys. With very small alloying additions, we can go ahead and we can knock down the irrecoverable strain by as much as 50% or so. And then if we add to that some thermomechanical processing, we can get very good behavior on these materials. I'll demonstrate that with the next slide. This is some earlier work that we did. And this is, again, using the ternary nickel, titanium, palladium alloy as the baseline, the 30 palladium alloy. If we add alloying additions to that, in this case we're adding 5% gold or platinum to the material, you can get a decrease of about 80% in the irrecoverable strain. Now if you take all three of those materials and mechanically work them, or run them through some kind of a training cycle, you can knock down the irrecoverable strain much more, by over 90%, though you can't really drive it, or in this case we haven't optimized the situation and driven it to zero. But the thermomechanical processing in this case represents basically training of the material, where we just applied a stress of 345 MPa and let it run through 10 thermal cycles. And in doing that, we deformed plastically the material incredibly, but we just let it do that for 10 cycles, and we built up a dislocation structure in the material. And then as you tested it at lower stresses, you got this better dimensional stability. The other way of doing something similar to that other than training would be to cold work and anneal the material, and it would give you similar results to that. So if I could have the next slide. We've done a lot of work on the palladium alloys. Unfortunately, we haven't gotten the irrecoverable strains quite to zero in most cases. Another one of the systems that we've been working on offers a lot of benefits compared to some of these other systems, and that's the nickel, titanium, platinum system. And it's unique for a number of reasons. If I can have the next slide. This is now transformation temperature, again, as a function of stoichiometry or titanium content. As I showed you before, nickel, titanium, as soon as you go nickel rich, transformation temperatures drop off like a rock. That happens also for the nickel, titanium, hafnium and the nickel, titanium, palladium systems. So if you're trying to develop a high temperature shape memory alloy, you certainly can't work on that side of stoichiometry because you're not going to have a high transformation temperature. The platinum alloys are different. You don't have that major loss in transformation temperature as you go to the nickel rich side. So that opens up a much broader range of compositions for which we can work with and offers a number of very interesting things along the way. If we could have the next slide. This is just kind of a review of the various phases that will occur other than the martensitic austenite phases in the titanium nickel platinum system. If you start very nickel rich, or very titanium rich, excuse me, you'll get titanium 3 platinum and basically a Ti2 Ni phase. Those are bad phases. They do absolutely nothing for you. They form interdendritically during the melting process. You can't dissolve them. You can't do anything with them other than break them up. As you get closer to stoichiometry, you lose the Ti3 PT phase, but you still have Ti2 Ni phase. And again, that's not a beneficial phase. It hurts your fracture properties. It hurts your fatigue life. As you hit stoichiometry, you basically are left with just a single phase material. The black dots in the pictures represent carbides that are due to the melt process that we use. We use graphite crucibles. But the second you go nickel rich, you develop a new set of precipitate phases. One is a new phase that's never been identified before. It's a very unique ordered structure of titanium, nickel, platinum that I'll talk about in a couple minutes. And then as you go further nickel rich, you get basically a Ti2 Ni3 type phase in these alloys. Now the difference is that on the nickel rich side, these precipitates are workable. We can put them in solution, we can reprecipitate them out through heat treatment, we can control their size, their volume fraction, and their distribution in the material. So these can be good actors for us. So if we go to the next slide. If we work very close to stoichiometry, in this case we have something that's slightly titanium rich, and we have something that's essentially stoichiometric. The aim composition is 50 titanium, but realizing the fact that as you aim for a 50% titanium alloy, you're going to lose a little bit of titanium. So this alloy in reality is a hair on the nickel rich side of stoichiometry. You see that the load biased thermal cycle characteristics of the two alloys are completely different. Now this is less than a 1% change in composition for these alloys, but you have a very large difference in the way strain accumulates or develops in these alloys. You can see that better in the next slide. Here we're just plotting the transformation strain as well as the irrecoverable strain for the two alloys shown in the previous slide. The alloy with the aim composition of 50% titanium shows almost no irrecoverable strain over a large stress range. It's basically inherent and it's inherently dimensionally stable, which is very unique to most of the shape memory alloys that I've ever seen. The alloy that's slightly titanium rich shows a larger amount of irrecoverable strain, but that strain level is about the same that you would see in binary nickel titanium at room temperature that was processed in a similar fashion. So for a high temperature alloy, that's not bad. And then the transformation strains, unfortunately, the alloy with a very good irrecoverable strain has lower transformation strain, and we want to be able to improve that, but we can do that through thermal manipulation of the alloys. So if I could have the next slide. The difference between these two alloys, if you just look at the diffraction spectrum, and these are neutron diffraction spectrum taken at room temperature, the x-axis is the same in both of them. What you see is that the alloy that has the aim composition of 50 titanium has much broader peaks than the other one. What this implies is that there's much higher internal or residual stress in the material. And this would be, again, due to these precipitates that we're talking about. So if we have the next slide. These very fine precipitates that you get very close to stoichiometry, but on the nickel-rich side, are extremely fine, essentially plate-shaped precipitates. You can see a couple of them edge on and a couple of them basically in the plate condition. They're on the order of 30 nanometers in size. They're extremely small. And as you would expect, with a very fine precipitate, you would expect a very high strengthening in the materials. And that's actually the case that you see in the next slide. This is just hardness as a function of aging time for these materials. If you solution quench, basically drive the precipitates back into solution, you have a very low hardness. And as you heat treat these alloys, there's two different ones here, one more nickel rich than the other, but as you heat treat these alloys, you get a very significant increase in hardness with peak aging around 3 to 5 hours in these particular alloys. So if I could have the next slide. The precipitate phase has been kind of bothering us because we haven't been able to characterize it. It's unlike anything that we've seen in the past or have any kind of an experience with. So these are actually very new results from Ohio State, Mike Mills' group there. And what you have on the right is an image using their Titan scanning transmission electron microscope, and you're actually resolving individual atoms in this case. The white shapes that almost look like dumbbells, those represent 2 platinum atoms. So if you look at that type of imaging and try to figure out what's going on in the particular alloys, again go back to an 011 perspective of the materials. Again, the titanium atoms would reside on one site, which are the blue atoms in the model. What's happening is that in the parent phase, you have platinum atoms now ordering within the B2 structure, but they're doing it in a way that I've never seen before. You actually have 2 platinum atoms, then 2 nickel atoms, then 2 platinum atoms as you go along 011 directions in that particular plane. So you have basically a higher ordering reaction that's going on in the parent phase, causing these extremely fine precipitates. The other thing that's unique about these precipitates, if I could have the next slide, and this was something that we basically had trouble with initially, is that the precipitates themselves didn't have that much of a compositional difference from the matrix. But now that you understand this higher ordering reaction, we kind of understand that. In the upper left-hand corner is a 3D atom probe sample, atom probe tip. The circles indicate where two of the precipitates are. The material in between is the matrix. If you look at the line scans, the compositional line scans across the bottom, there's very little change in the composition of the precipitate as you go from the two precipitates to the matrix in between. You do get a little bit of increase in nickel and a little bit of decrease in the platinum content of the precipitates themselves. But that would actually lead to something that would be very useful because we put the platinum in there in the first place to raise the transformation temperature. So if we're basically adding or forming precipitates and then kicking platinum out into the matrix, we should be able to increase the transformation temperature further. So if we have the next slide, that's exactly what you see. As you age these materials and form larger precipitates, you get a very significant increase in the transformation temperatures for the material because of what's happening in the partitioning of the platinum from the precipitate phase to the matrix itself. If I could have the next slide, please. Now, since we're trying to develop high temperature alloys, the question is how high can you go? This was the first two individual graphs are the ones I showed you earlier on, trying to make the point that shape memory behavior doesn't represent load bias behavior. So we know that going to 30% platinum isn't very good in these materials. And again, I said I'd come back to tell you why. And we've covered this already, but I'll show you again. If you look at the bottom graph, it's basically the yield stress of what a binary nickel-titanium alloy would be. At the lower temperatures, you're basically representing the stress for detwinning. At the higher temperatures, you're looking at the stress for the austenite yield strength. You have to have this large increase in between to get useful work. For the 20 platinum alloy, that's the same type of behavior, characteristic behavior you see, though the detwinning stresses are even are much higher than what you get in binary nickel-titanium. But when you go to the 30 platinum alloy, the detwinning stresses go up even further. In fact, they're very high now. And the detwinning stress is now actually higher than what it takes to deform the austenite. So we're back to that original condition. We can't put any kind of recoverable deformation into the alloy. We can't detwin it, but at the same time, if you would go ahead and thermally cycle that material under load, you're going to deform it plastically because of the austenite deformation. So if we go to the next slide, let's split the difference and go to 25 platinum. And in that case, we still don't see very good behavior in these materials. But now if we start alloying, if we go back to the original concept, well, let's start alloying these materials to make the phases a little bit stronger. So we have alloying additions that we can add to these materials. And so if we take the same nickel-titanium 25 platinum alloy and add about 2% of an alloying addition, we can get a very significant increase in the work characteristics of these materials, and you get curves that look very similar to what you would see before, but now with transformation temperatures between 300 and 400 degrees C. And again, the reason for that, if you go to the next slide, is that we've increased the yield strength of that quaternary alloy significantly above that of what the ternary was. So we've gone and accomplished what we thought we would do. We strengthened the austenite phase. We've got a high temperature, much higher strength in the high temperature phase, and at the same time we really didn't affect the detwinning stress very much. So that basically allows us to create high temperature shape memory alloys. So if I could have the next slide. What we've basically found out from all this work is that once you get above about 300 degrees C, it becomes very difficult to create a high temperature shape memory alloy because of the basic characteristics of the individual phases. But there are things that you can do. You can start engineering materials now by adding alloying additions using solid solution strengthening and precipitate strengthening in order to basically develop an engineered high temperature shape memory alloy where you can begin to push the usefulness of these materials now to closer to 400 degrees C at least within the systems that we're working with. If I can have the next slide. This is just a summary then of the advantages of the two different systems that we've spent a lot of time working on, the palladium and the platinum containing alloys. Transformation temperatures, they're both a linear function of the ternary alloying addition, the palladium and platinum. However, the benefit with the nickel-titanium platinum alloy is that we can work in these materials nickel-rich. We don't have the stoichiometry limitation. That frees us up to do things with the microstructure. Ti2Ni is a bad phase. We're kind of stuck with that in the titanium-rich alloys, but we can't help it. All we can do is mechanically work and break that phase up. In the platinum-containing alloys, we can eliminate it. We don't have to worry about that phase. And in addition, we get phases that are beneficial. We get fine precipitate phases that we can go ahead and manipulate for strengthening concerns. In terms of dimensional stability, there's an issue, just like with binary nickel-titanium with the nickel-titanium-palladium alloys. But the alloys that are actually a little bit nickel-rich in the nickel-titanium-platinum system are inherently dimensionally stable. They have very good stability without having to do anything to them. The problem, of course, is the cost. Palladium is expensive. Platinum is just outrageously expensive. The thing was, when we started doing this work about 4 years ago, since that time, platinum's gone up 400%. When we first started working on these alloys, there were applications where you could go ahead and do a cost-benefit analysis. And you can say, all right, the alloy is going to cost me this much, but because of all the fuel savings I'm going to get, or because of other benefits, it's going to be worth it, and you would use these types of alloys. As the cost shifts, your cost-benefit analysis and the number of applications shift. But there are still always applications where you will get a benefit, regardless of the cost of the materials. If I could have the next slide. That's a little bit about what we've done in alloy development with these types of high-temperature alloys. What I want to talk about now is a little bit about the application of the materials and how they're used and integrated into structures. If we could have the next slide, please. The problem is, before you can actually utilize these things in components, you have to be able to process it in a useful form. So just being able to go into the laboratory and coming out with a little chunk or a little handful of material is not very useful if you can't fabricate it into a form that you really want to use later on. And the form that we've been using a lot in our demonstrators has been wire. So all along the alloy development path, and it's basically a parallel path, we've been doing processing studies and figuring out how to process these materials. We actually induction melt, and we do the induction melting in-house at Glenn for these materials. We used to do extrusion in-house, but we now farm that out. So we'll take the ingots that we induction melt, we homogenize them, we have them extruded into the rod, and from that rod we take the mechanical test samples that I've shown you all the data that we've generated. Or we can take those rods and have them re-extruded into finer diameter rod. And from that fine diameter rod we can do one of two things. We can have it machined into different rod or fine wire diameters, and that's kind of a waste, but if you're doing a quick demo and you need to get there very quickly, it's one way of doing that, and it's also something that we control in-house. We have wire grinding capability in-house at Glenn. The other thing that we've done is we've worked with a number of wire drawing companies to figure out processes for how to actually cold draw the wire. So we're basically pulling this material through a die and reducing its diameter by cold drawing. And we've been able to do this for most of the alloys that we've developed. So if we go to the next slide, this represents some of the things that we've been able to do. Since we've been able to make wire out of a lot of the alloys that we've processed, we've been able to then kind of incorporate the wire into different types of demonstrations, and just to get an idea for, or a feel for how the material works. Walking around this plot or this figure clockwise from the upper right-hand corner, the one application I'll talk about in a little bit more detail is a high-temperature inlet ramp. Basically, it was scaled to down to, but was designed for a supersonic business jet, an adaptable ramp. The next one is a small actuator that Mega Motors has made. In fact, this incorporates one of our nickel titanium palladium alloys, and they actually, I think they still have a movie of this thing actuating in boiling water. Again, conventional alloys won't work under those types of temperatures, but this is actually a very low temperature for the alloy that's in the actuator, and it actually cycles quite quickly. The actuator itself weighs less than an ounce. It's capable of 4 or 5 pounds of force and a 1/4 inch of stroke. So that's a type of a commercial motor or actuator. The lower right-hand corner is a flow control device that we were developing. Actually, it was a very specific application. At one point, there was another group testing a T-700 engine, which is a small helicopter engine, and they're trying to look at flow instabilities and trying to figure out how to prevent stall. So they were using little surge control rods, or little rods that they would induce or push into the centrifugal compressor to create turbulence and reattach the flow. And in the test cell, these actuators were hooked up to 1/4 inch pneumatic lines, and there were about 10 of them, so you had all these lines coming off this test cell. Well, that wouldn't fly, both literally and figuratively, so wanted to see if we could actually make a device that would fit into a real engine and serve the same purpose. So we developed a little flow control device. First generation operated under the force conditions and stroke that we needed. The problem was it had a little bit of a tail. There was about 10 inches of wire that came out of the back end of it. It was in a flexible motorcycle type cabling, so it was anchored at the end, and we could move it around and fit it within the engine, but it didn't give us the satisfaction that we wanted. So then we came up with a secondary design based on springs. And we actually developed and shape set some high temperature shape memory alloy springs. We had a student that came in and did a master's thesis on characterizing those springs and the spring properties. And based on the properties of the springs that were developed, we never actually made the actuator, but based on the properties of the springs, we could probably pull off the same thing in terms of actuation capability with a spring with about 2 coils, 2 wraps. So you could really shrink your actuator down by using different forms of the shape memory alloy. And then the final demonstration was a high temperature core exhaust chevron, which I'll also talk about in a little bit more detail. If I could have the next slide, please. This is the high-speed inlet ramp that was basically developed and tested by Continuum Dynamics under an SBIR funding. And what we did was we supplied them with the nickel titanium platinum wire in order to do the demonstration. The whole purpose here was to develop a ramp, high-speed inlet ramp that we could go ahead and translate back and forth as well as change the angle to it depending on the flight conditions. On the left-hand side, it's just a benchtop model with all the shape memory alloy underneath, and that model was capable of both translation and angular change. But when we went to the wind tunnel, which is the bottom one, we just basically looked at the translation of the ramp. So if we go to the next slide, we started out with basically an actuator mechanism based on an X design. What we did by doing that is basically you pull on, in the upper right-hand corner, you pull on that X mechanism, and it multiplies your strain by a factor of 4 by basically angling out. This whole thing had to fit within a hardware that was about 1/2 an inch deep, and in fact the entire thing was only about 6/10 of an inch thick. That went in the whole model that went into the wind tunnel. The model was loaded into a wind tunnel at Princeton, and we were able to generate about 3/4 of an inch ramp movement with the shape memory alloy. If we go to the next slide, this shows the some of the results of the wind tunnel testing. We were able to get up to a speed of about Mach 0.66 because we're using air at basically sea level. If you took that into account, the dynamic pressures at altitude would be equivalent to about a Mach 1.8. But under those conditions, the Mach 0.66 flow, we were able to move the actuator about 3/4 of an inch. But we couldn't exceed that level of speed in the tunnel because of all the excess friction in the linkages and that. So what we did was we redesigned the actuator. So if you go to the next slide. Instead of the X mechanism, and this just kind of gives you some of the numbers of what you have when you're using and designing shape memory alloys. We had a 44 mil diameter nickel titanium platinum wire, and it was capable of about 1.2% strain. That's the strain that was induced into the wire. And it was basically causing or exerting 24 pounds of force. When you translated that through the mechanism, you were getting about 7/10 of an inch of stroke as well as about 6 pounds of force. What we did then was kind of revise the design. We made a lever arm out of it so that when you pulled on the arm, you basically pushed the ramp in. When we did that, we lost some of the stroke capability so that we were only able to get about 1/2 inch of stroke, but now we were able to do that with about 14 pounds of force in the end. So if you go to the next slide, we put the new model back into the wind tunnel. We were able to test it up to speeds of essentially Mach 0.9, and we had no problems with it. The problem was really with the model and the testing. We didn't reach the limitations of the model due to the shape memory alloy. What we did was we were creating blockage over the model itself, so we can never break supersonic over the model. So we're going to reconfigure the model itself and go back and do some additional testing for that. Now the thing is that it's not unique to go in and have some kind of a model in a wind tunnel and some kind of a ramp actuating or moving. The point here for this particular work is that the motor for this particular ramp really was nothing more than a piece of wire. So this is not wire hooked to a motor. This was your motor. This was the wire used to make that ramp move. This is what, shape memory alloys are used for. So if we go to the next slide. Another application for shape memory alloys is in these chevrons, and this is something that Boeing and others have been looking at. In fact, Boeing has done a flight demonstration for these materials. But the chevrons, both on the fan exhaust and the core exhaust, dip into the flow stream, create turbulence, reduce the noise on takeoff, but you have a performance penalty when you hit the cruise condition. So this is an ideal application, again, for SMAs. You have a very thin-walled structure. You want these chevrons into the flow stream during takeoff, removed from the flow stream during cruise so you don't get your penalty. It's one cycle per flight. You have very limited space to put these things. So it's one of those applications that have been studied in more detail. So if you go to the next slide, as I said, Boeing has done this with actually a full-scale flight demonstration that they did back in 2005 under their QTD program. Each one of those chevrons or those triangular objects was basically operated by 3 very large plate-shaped SMA actuators. And they ran it in various configurations. They basically allowed it to work passively. They actuated it actively because each one of those plate chevrons shown on the inset had a heater attached to them. And they also did parametric studies, and as just putting in certain chevrons and leaving others out. And what they found by doing that was they could reduce shock cell noise by just having certain chevrons in place during the cruise condition. Now, if you go to the next slide, we decided to take a different tack in designing our chevrons. This is, again, work done by CDI under SBIR funding, and the actuation was done with nickel titanium platinum wire, again, one of the high-temperature shape memory alloys. Instead of trying to bend that curved chevron, what we wanted to do is reduce the stiffness, so we put a cut into it. Very simple thing to do. By putting the cut into the chevron and reducing the stiffness, it basically is 5 times more efficient, or it takes 1/5 the force to basically deflect that chevron. What that means is that if we scaled up and used the shape memory alloys that we developed, it would only take about 4 or 5 wires instead of 3 large plates to deflect a full-scale chevron. The bending is very reproducible, and it's purely elastic, so you'd have long life out of the thing, and it has a built-in stop so that once it comes down and meets, it stops with a certain depth of penetration. Now, next generation chevrons along this design have already been built under Prop 21. Basically, CDI, GE, and Spirit Aerospace worked on that based on the original designs we have. But if we could have the movie, I'll show you the operation of this chevron. Basically, all you're doing is squeezing across the tip where the cut is. So if I could go ahead and have the movie, as you squeeze across the tip of the chevron, you're basically forcing it down and causing it to deflect. So it's, again, a very simple design. The shape memory alloy itself is actually situated behind the chevron itself. So that's just straight steel wire that's across the tip. And the actuation force is applied by the wire that starts basically off-screen there by the shape memory alloy. Basically, this is the connection between the steel cable and the shape memory alloy itself. So if we could have the next slide then. We used this model in a number of, again, demonstration conditions. We put it again in the Princeton wind tunnel. We're able to actuate it with the desired flexion, which was 0.2 of an inch deflection against Mach 0.6 flow in the wind tunnel at Princeton. If we could have the next slide. We also inserted the chevron into a coaxial flow test rig at the University of Cincinnati, so we had hot core flow now going across the chevron, basically 100 degrees C gas, which was very low in temperature compared to the capability of the alloys, but it was the highest the rig could throw out. But trying to get closer to a high temperature demonstration, and again, with the coaxial flow and the hot core exhaust, we were able to generate the required deflections for the material. So if I can go to basically just finish up here, if I could go to the next slide. What I've tried to convey today is that solid-state actuators based on shape memory alloys and nickel titanium have basic limitations. One happens to do with dimensional stability. The other one has to do with their real use temperature. So we've been trying to develop new alloys to overcome those, both in the case of the binary alloys. We're starting to work with new nickel-rich compositions and heat treatments to adjust things for some work for Boeing, stuff I didn't have time to talk about today. We've also been developing viable high-temperature shape memory alloys based on nickel-titanium ternary compositions. Some of the alloys that we've been working with the most are palladium and platinum-based, but some of the newer work is also on hafnium-containing alloys. And up to about 300 degrees C, you have relatively little problems with these alloys, though you have to realize they're very early generation materials, and we don't know a lot about their long-term durability. We're just trying to, right now, optimize and realize final compositions. But if you want to go beyond about 300 degrees C, it's going to take a lot more engineering in these materials. You're going to have to get a lot smarter and actually have an engineered material using different forms of alloying and combinations of alloying and precipitation strengthening. So if we can go to the next slide. Basically, just one of the couple of things I want you to remember from this talk is that when developing shape memory alloys for actuator applications, transformation temperature really is just there as a guide. It's more or less the minimum requirement that you need for the materials if you want to develop a high temperature shape memory alloy. Shape memory behavior itself under stress-free conditions is absolutely meaningless. Unfortunately, that's what 95% of the people out there measure. If you really want to measure the work-related characteristics of the material or get an understanding for that, then measure the work-related characteristics. That's really the takeaway there. And if you want to make a better high-temperature shape memory alloy, the basic thing you need to do is prohibit any kind of dislocation-mediated processes or deformation processes from occurring in the material. In terms of processability, if you can't process the alloys in a useful form, they're not really useful. So we've fortunately been able to work both tracks, alloy development and processing in these materials, at least enough to get to the point where we've run some demonstrations to show that high temperature shape memory alloys are actually viable today for some high temperature applications. So if I can go to the final slides. The work that I've done for the last 2 years is basically supported by fundamental aeronautics, both the supersonics project and the subsonic fixed wing projects. Prior to that, it was split between IR&D funding at Glenn Research Center as well as the various aeronautics projects that kind of existed prior to Lisa Porter being here. Finally, if I could have the last slide. The work that we've done, the work that I've talked about, wouldn't be possible without the help of the group or the team back at NASA Glenn Research Center. Primarily Santo, Glenn, Anita, and Daryl. We've also been working very closely, and they've given us a lot of insight and applications of shape memory alloys, the group at Boeing. We owe a lot to Continuum Dynamics in terms of the demonstrations they've run for us. And also, as well as like to acknowledge all the different universities that we're starting to work with, but in particular, Raj V at the University of Central Florida in terms of all the neutron diffraction work that he's done, allowing us to understand some of the more fundamental issues of the mechanisms behind shape memory behavior. So with that, I really thank you for your attention. I hope I didn't talk your ears off too much here, so thank you.
Thank you, Ron. Hi, I'm J.D. Harrington. I'll be handling the question and answer portion of today's session. If you have a question, if you would, please wait until we get the microphone to you and then identify yourself before we begin. Here at headquarters, do we have any questions? I have one back here in the back. I have one right here. Go ahead.
I'm Farah Tamasebi with Aviation Safety.
Yeah.
Most of the examples you showed involve generating force. For shape memory alloys that generate torque, do you usually use a transmission such as slider crank or rack pinion? Or is it possible to use torsional springs?
Actually, we use tubes. In order to generate a torque, we use torque tubes. So if you wanted to generate a large force in some type of a torque application, there's a couple ways of doing it, but the straightforward way is to use a torque tube. The other is that you could use a wire acting on some type of a gearing, but the torque tube is the way to generate the high forces.
Okay. I believe we have one back here in the back corner.
Caitlin Eubank from NASA Goddard. I guess my application is more low temperature. I'm working on an actuator to replace pyrotechnic valves on propulsion systems. So it's a normally closed flow valve. It uses about 100 C actuation. But we use half-inch diameter bars. And I guess I was wondering if you had any characterization studies on percent recovery and force produced from bars versus wires in the low temperature regime.
When we first started working out in the shape memory alloys, we're pretty much geared to working only on high temperature materials because that's what the funding was for, and doing anything that people thought was conventional was kind of out of the question. So we haven't really developed the database for those particular materials, but I know Nitai Aerospace developed some very good materials for those types of applications, but I haven't seen any data sheets. I don't know. You could ask them to see if they have data available.
Sorry.
Did they have data sheets for you?
No, they didn't have the data sheets, which is why I was wondering if the characterization
We have not.
studies.
We've only characterized one of their materials, and that's the one that had really the highest work output capability.
Gotcha. Yeah, ours is enough work to break the titanium seal, which is a large amount of force, but
Right.
thank you.
All right, we have one more here.
What are the advantages and maybe disadvantages of shape memory alloys to piezoelectric actuators? How do you compare them?
Piezoelectric actuators and shape memory alloys work in two different regimes. There's really almost no cross-fertilization between those. The piezos are very rapid actuation, kilohertz type things, but extremely, extremely small strains and very small forces. So they wouldn't be used for moving something like a chevron or something even larger than that. The difference is that when you get to the shape memory alloys, you have the larger strokes, you have much, much higher forces, but much slower actuation because everything is thermally driven. So they're really complementary type actuation systems, one just to be used in different regimes. They really don't overlap.
Thanks, Ron. We're going to go now to the Glenn Research Center for a question.
Hi, Ron. Malcolm Stanford here at Glenn. I have a couple of questions. One is, do you have will you get some sort of hysteresis in the strain you can recover in this shape memory effect? And the second, if I can slip it in, is can these alloys be produced by traditional powder metallurgy techniques? Just to maybe address some of the engineered aspects that you could get by that set of techniques? Thank you.
Yeah, I'll start with the second question. You can produce these materials by powder metallurgical techniques. We've done it for some of the, in fact, we've done it for one of the high temperature shape memory alloy, nickel, titanium, palladium materials. One of the problems there with such as is really your yield for your powder processing. Your yield is probably about 50% of your original melt. So when you're working with these precious metal containing alloys, to have such low yields when making the powder is a major disadvantage, but you can produce these materials through conventional powder metallurgical techniques, and it works quite well for them. The first question, I don't quite understand what you're asking about in terms of the hysteresis of the strain.
Hi, my name is Amr Bez from University of Maryland, College Park here. I noticed from your slides two things. The strains are very low, 2 to 3%, and also the hysteresis loops are very small. Are these done on purpose or not? And then the second question is, are you planning to use this material in pseudoelastic form for damping application at high temperature or not? Thanks very much.
In terms of what you see, the data is the data. We've noticed that for the high temperature shape memory alloys, the hysteresis tends to be smaller than what you generally see in binary nickel titanium alloys. At the same time, the transformation strains are a little bit smaller as well. And the real reason for that, if you saw some of the plots, is that the detwining stress is very difficult. It's very difficult to detwin these materials compared to nickel titanium. You're looking at 50 MPa versus maybe 200 MPa. So you tend to get less transformation strain out of the materials, but we've not really done anything to optimize that situation. And so that's why in many of the cases when you're working with 2-3% type strains, you use some type of a strain multiplication mechanism. The other difference is that you can get much higher forces out of these materials. So in that case, you can use strain multiplication mechanisms for that. Your second question, I forget now.
Superelastic hysteresis
Oh,
performance?
superelastic behavior. Superelastic behaviors, that's an interesting question. And what we've found with these materials is that you really don't see superelastic responses in these alloys. When you go ahead and load them up and get basically stress-induced martensite above the austenite finish temperature, that martensite is stable, and what it requires is, so it does not return once you release the stress on it, so it's not really superelastic. You have to actually heat it up another couple degrees. So if you actually release the stress and then gave it a couple degrees temperature, and just a couple, 2-3 degrees, then you'll recover it. But it's not a true superelastic behavior. It's kind of a pseudo-superelastic.
Okay, I believe we're going back to Glenn right now for a follow-up question to the original.
Okay, hi, Ron, Malcolm Stanford again. I'm sorry, let me rephrase how I asked the question. After many cycles, do you start to lose the strain, the recovered strain that over many cycles, do you lose
All right, I
the
understand the
strain
question now.
recovery?
One of the problems with shape memory alloys, especially the conventional nitinols, is that as you continually cycle them under a constant stress, what happens is you start losing transformation strain with cycling, and it'll eventually, I think, plateau, but you do get a significant decrease with increasing cycle time. One of the interesting things, at least from the limited data we have from the nickel, titanium, platinum system, is that you do not see that decrease in transformation strain with cycling. In the palladium alloys, you do get some of that, but in the platinum alloys, that's another one of the advantages of the system, is you do not get a degradation in transformation strain with continued cycling.
Thanks, Ron. I believe we have another question here at headquarters.
Yuri Flom, NASA Goddard. Ron, as I recall, back in mid-90s, there were at least 2 engineering roadblocks or hurdles with application, with practical applications. One is that uniform heat delivery to a component which is slightly bulkier than the wire. So if, for example, you have a 1/2 inch or 1 inch rod, and you want to have a uniform transformation across the cross-section, how do you deliver heat uniformly to entire bulk? And number 2, heat delivery, most common, I guess, way or method was electrical current. So people had a hard time with degradation of a shape memory alloy at the contact points. So have there been any progress or advances since then? Thanks.
For fine wire, it's practical and very common to heat the materials resistively through joule heating. I'm not familiar necessarily with the loss in behavior or with the contact points. That might just be simply a crimping issue or an issue with how the contacts are actually made. I know that a lot has been done since then in terms of how to crimp these particular alloys. In terms of the second question, in terms of heating these materials, if you're really looking for low duty cycle, in the case of some of the things that Boeing is working on, they basically just build heaters into around the shape memory alloys. They just put basically heat tape right across the plates or inside the center of the torque tubes, whatever they're doing, and then they heat using external heaters. And basically, if you're looking at just a measured, generally slow response, there's no problem doing that.
Thanks, Ron. I believe we have time for one more question. Tony, you're at headquarters.
Tony Strasser here at headquarters with Fundamental Aero. Ron, I have a question about scalability. I know that Boeing uses actuators that weigh several ounces and they generate several hundred pounds of force. And most of your work that you showed us today had to do with fine wires. Is there a limit to shape memory alloys? Can you generate as much force as you want simply by making a larger bulk of the SMA material?
I don't believe that scalability is an issue. You can just basically get a larger force by making a larger actuator. And again, the key goes back to what the last person said, is how you can heat that material. But I believe now, if I'm correct, Boeing has actually developed some torque tubes that can basically deliver several tons of force. Very large actuators made out of shape memory alloy.
And I think that's going to have to do it for today's presentation. If you have any other further questions, you can email me or Beth Dickey and ARMD, and we'll get them to Ron for an answer. I'd like to thank Ron Noby for his time from Glenn Research Center. And if you have any questions about this or any other NASA aeronautics project, visit us on the web at www.aeronautics.nasa.gov. Thanks and have a great day.